Well, welcome back to our last and perhaps the most important part of this event, which we are going to put in the hands of a venture capitalist, entrepreneurs, and innovators. So as you have seen, this conference was an attempt to synthesize multiple points of view from multiple different communities. So we thought that to chair this panel, we could either get a scientist, we could get a technologist, we could get an entrepreneur, maybe we could get head of a foundation, or maybe we could get a philanthropist, or maybe we could get a professor who's immersed in technology. So there are many, many such choices. Luckily, it turns out that we could get them all in one person. And ladies and gentlemen, that is Dr. Jerry Schwartz. Let me tell you a little bit about this unique individual. Dr. Jerry Schwartz founded and led the Symbol Technologies all the way from zero to a public company, which very recently was acquired, by the way, by Motorola. And he served as the chairman and the chief scientist of Symbol Technology. So that's the entrepreneur for you. Now, how about technologists and scientists? He has authored or co-authored over 200 patents and many different publications, winner of National Medal of Technology. He has received many, many, many awards. IEEE Tech Island Award, IEEE Wheeler Award, is a fellow of IEEE. The prestigious Ernst Weber Leadership Award, IEEE Third Millennium Award, Eureka Award from the New York Academy of Sciences. So that's the technologist for you. So that's the first part of Jerry's career. After he retired, Jerry has been serving as a trustee for the Cold Spring Harbor Laboratory and as also trustee for the University of California at San Diego. He has several other affiliations, which I'm not going to talk about now, but I could let you read. Now I turn to the final and the most important contribution that he's made lately to humanity by starting the Schwartz Foundation. The Schwartz Foundation has really brought under its umbrella many universities: UCSF, Brandeis, Salk Institute, Columbia, now Princeton, Yale, and I may forget Cold Spring Harbor, Caltech, and I may have forgotten one, so Jerry, forgive me for that. And so, this is really, really a unique leader, and to listen to his perspective and to have his leadership in, taking us to the future of cognitive computing is what we seek. So ladies and gentlemen, please join me in welcoming Dr. Jerry Schwartz.
Just give me a minute. In the back? Okay, good. I got water. I have notes scribbled in the middle of the night. So I'm just about set, and I have, in fact, more notes than brains. So I'm just about there. Dharmendra, thank you very much for your kind introduction. And I will be introducing the other panelists. So I think what I would like to do is start with just a few points of housekeeping. And at the same time, I have some prepared remarks and some PowerPoint as well, which express my own perspective. So you have a little bit of leeway in being able to just not moderate, but express some of the things that are contained within all of us. I took that discretion. The presentations from the panel will be about 10 minutes long. And going back to Dharmendra's remarks, and specifically his remarks about me and about just about everybody here, certainly all the presentations, or most of the presentations I heard, is the whole interdisciplinary, cross-functional, convergence nature of what is going on in quote-unquote this field. I think it's a lot broader than that. I think that in this century, the sciences are converging. Who says biology, physics, and chemistry were ever different other than in the 17th century as they started? You start with boundary condition problems and you don't understand them, and then they merge and you go to the inner core. Education itself across so many fields. Look at finance and mathematics coming together. Hello, quants out there and hedge funds. So I think there is a very fundamental set of things that are happening worldwide, and they do involve, indeed, a lot of areas. I think so many of the presenters had backgrounds that came from one area and became fascinated in another. I'm not going to be so reductionist to say that a human being is just an application of science or of physics or of mathematics, but it certainly seems from our own notions and feelings of coming from areas of work that we did over the years that were very attracted, so many of us, so many people, in so many ways, to thinking about the brain and thinking about it. I think James Anderson described it well yesterday about the cognitive aspects, and literally in his simulation going from a von Neumann model and saying, hey, logic's great. The brain is, as we all know, a very different model. And how do those pieces wind up coming together? How do you produce something that can make decisions and judgments? And if Professor Zada was here, I'd call it fuzzy logic 6.0 or 8.0 or something. Not so different as these things evolve. And that's really a very amazing combination. So not a coincidence, as Dharmendra described, that I'm moderating and chairing this panel. It's a real challenge to everybody in this room to even attend and listen to the presentations. There is no way, as a few of our speakers noted correctly and said, gee, I know what I know, but I also know what I don't know. And that's the truth. All of us are in the same thing. And there's kind of a Venn diagram overlap, but there's nobody that really has the intersection of the sets all together. So if Dharmendra made you think that's the case, he's wrong. So actually I'm just getting my union card in brain science and doing things in non-conscious processing, and what's fun for me is mathematical physics, so I approach it from what's called computational neuroscience, and yes, there are 10 universities and institutions that we support and are doing the kind of theoretical work with them that is really important. So the panel has that set of characteristics, and I think you're now challenged with one additional dimension which threaded through some of the presentations, but in fact will be big time here. So you've got real entrepreneurs, several of them from companies that are new and developing and growing, which is what's amazing about this field. The field is complex and difficult. Those words mean two different things to me, okay? But it's complex and it's difficult, and as it comes together, it's very exciting. The growth potential, the whatever business nonlinear differential equation attractor networks that are working to get people into this field as an equivalent, as Steve and I were discussing before, is a very real thing as things do come together. And Steve Jurvetson, am I pronouncing your name right? I don't think so. Jurvetson. Okay, so I should know better. As a matter of fact, I'm a totally West Coast person. My brain and my mind and everything else works that way. In fact, I happen to be on UCSD's Board of Trustees after doing some research there over the years anyway, not looking to be on anyone's additional board and so on. And so they identified me as their East Coast poster child. So, okay, so, but the East Coast does get it much of the time. So I really do wind up living both worlds, and I will try to do that job to blend things together. I like to run an open show, so it'll stretch out to the audience and questions and comments during it. It may not be as disciplined as structured as you might like, and other moderators do it. It's not known to be my greatest strength. So I do want some interaction, and it'll go heavily up and back to our panel members. The Q&A will happen as I make my presentation. We're first going to bring up every panelist. As I said, that'll be allowed 10 minutes. And then we'll go into the Q&A. So bear with us, because there is 2.5 hours that has been provided by our organizers, and I think we're going to need every minute of it. So let me talk a little bit about what and how I see things in the world I came from and the world that I find myself in now. And it's got a lot of ingredients, as we know, really, truly challenging. This slide is just a simple representation that it truly is a frontier going forward, and a very exciting one, highly interdisciplinary. I'd make a pitch for the fact that the engineering disciplines need to be here. It's not just the systems engineering approach and thinking, which on the one hand, if my heart or my mind or thought processes tend to come from the world of a physicist, if you're going to get stuff done, if it's going to work, and if you're going to be someone who wants that kind of action and believes that that's important, then the world of engineering has a lot to say, not just from its technology, but from an approach and a style, which is even different than physicists. So if you ask a Parthomitra at Cold Spring Harbor Labs, he's a huge advocate, not just at circuit and network level of studying the brain, but also on thinking that that kind of an approach to brain science is really important. If you talk to a Rahul Sapeshka at MIT, Rahul worked also, Lloyd, on things, as you may know, on auditory and cochlea and whatever, and made some really good contributions. He couldn't wait to go build something. Okay, so this is a huge thing. You learn from building. Even if you don't build, the thing that is so interesting is that the notion of man and machine is literally changing as we speak. So whatever existed in our thought processes for, let's say, prior to 10, 20 years ago, now this wave is coming on that it's a very different thought process that we wind up having. And building things on the machine side, things that people do at companies in industry, things that I did in wearable computers that sold 28,000 to UPS, or handheld scanners, or the combination of these ingredients in handheld computing and Wi-Fi. We actually did Wi-Fi in 1990. We were the first ones to do it at retailers, et cetera, and combining that with voice over IP. Building these things matter. You learn an awful lot, but it's kind of iterative, from the theory back to the practical application, and from the practical application back to the theory. And I see people doing that, from theory to lab to building things, and I think it's a very productive flow. Another point to make, and not to get carried away on an engineering perspective, which is just part of me and part of many of us and how we think about it, I never forget reading a book from 1880s, which my uncle had given me, by Oliver Heaviside, if any of you know the name. It was on operational calculus, and he was the first one that took strange-looking circuit-type things and wasn't even doing transform things per se, but he found that putting a P in and replacing it reduced the whole thing to algebra. And mathematicians for years, if any of you know the history of delta function distribution theory, and I won't get the name right, there was a Frenchman, Schwarzbart maybe, out of Paris in 1944 that first proved an existence theorem and made it okay. Even the physicists doing electromagnetic theory were staying with Green's theorems and other things without using modal analysis approaches. So there is an engineering approach to things that is indeed helpful. Once you start thinking engineering, once you start thinking technology to supplement the science and sciences that constitute brain science, you start thinking about devices and business and usefulness and killer apps and whatever. So there is a fit, and I think our organizers have to be congratulated to recognize that from an innovation point of view, from a convergence point of view, and from the fact that this is going to be actually very helpful to put these things together. And it's the real world, and it really is happening in a very, very powerful way. Okay, so let me continue. The world that I stay closely involved with personally is computational neuroscience. So it is computer science, neuroscience, and it's the theoretical aspects that I'm most interested in. And I am, I think, having problems with this. Okay. So the clinical, just to make a comment on clinical, unless the theory and fundamental principles, in my mind, get straight, not only in understanding the brain better or understanding whatever you're trying to do better, all you're going to have with surgery and with drugs is adverse reactions. You're going to do something with a shotgun and not with a rifle, and that's not good enough. So you really do need to model it. You really do need to get at the details, and then good things will happen even on the clinical end. So high-tech, med-tech, the kind of companies, the kind of technologies, really are very fundamental coming from that convergence. Looking at the brain, looking at the computer first, I mean, I know when I do something, I think of my Open System Interconnect, my OSI stack, and people who are good programmers, much better than me. I notice how they do their flow charts coming out of it and so on. It's a really useful framework no matter what, either high-level thinking about it or even down at programming levels. So many of us, starting with Terry Sinowski, who thought of it as multi-scale, and we just ran a conference last September that he had hosted and chaired on multi-level, and we'll hear more about that from our first speaker after me is going to be Tony Bell, who will talk about levels. It's a very interesting thing to think about, even at a, if anyone has an extra laser pointer, because this isn't working so well. I don't think my finger is blocking it. I've been known to do that. Okay, you want to just check that?
It's okay.
It's okay. So what am I doing wrong? We won't bother figuring that out. Okay, good, better. So going from molecular to neuronal, circuit, network, whatever, what's very interesting because, I mean, what are we talking about here? We're talking about physics plus evolution is one way to look at it. And you certainly can't leave evolution out of it in terms of understanding the brain. So we're looking at pieces that when you get up, evolution ain't stopping. So as and we didn't evolve as a standalone, did we? We evolved in terms of human interaction, social interaction, for all the obvious reasons. But nowadays, it's not just physical, it's electronic, and it's internet. So stay tuned. There's going to be evolution that's happening up to layers and levels, I think, that are going to continue over the millennia, basically. How quickly these things happen, how quickly we understand it, and how quickly evolution, certainly of us, are not going to change, isn't going to happen. How machine and man interact, and we'll talk about that in a minute, will be very interesting. So, I don't want to dwell on this, but I do want to move on and say that, so when we think of a brain framework and we think of a computer framework, you, of course, as several of the speakers went to compare and discuss, etc. But brains are not computers. There's no clock. We have no clock. We have no compass. And yet we do a great job of kind of getting around in the world, both brain dynamic-wise and the real world of space and time. And, of course, these are things we are beginning to understand and study. But they are supported by the same physics. And they do have elements in common. Carbon and silicon are different, and low speed and high speed are different, and parallel processing is where we're headed. And no, it's really a hardware-centric type model with perhaps an adaptive operating system. And again, other people made some really insightful comments about that. Tough stuff. This is not easy stuff, any of it. Either the modeling or the simulation, any parts of it. They're complex and difficult, as I said, and we're still at a stage where there's not a hell of a lot of understanding of the functionality. It amazes me. I thought when I knew very little, you know, there's a law of this, I don't know which one it is, but when I knew very little, I thought we understood a lot. The more I learn, the less and less I know we know. We have a long way to go to understanding things, and most people who work in this field own up to it very quickly. On the other hand, on the simulation end, there's stuff to draw on, and there's exciting things happening on that. Out to devices and simulations and fabrication coming from technologies that we do understand. And there are things that are really going to happen, whether it's an electronic nose or an artificial retina. There will be devices and things that will commercially happen and relate to business in the future. In fact, I would actually ask a question right here of our panelists and audience. I remember reading an article in New Scientist called Mind Chips, mostly wrapped around Corbena Bohan's work. If anyone has an update, I haven't heard it for a while, of his progress. Or maybe Dharmendra on what Henry Markham's doing in Lausanne on his project in simulation. I don't have those updates, but I know that these are good things, worthwhile things, and things that we'll learn from. A little closer to my world, and I started looking at a large-scale model, because after all, someone needs to give me some equations to work with. That's how I learned to function. That's what we all learned in school, okay? So our whole education, you develop from there, but from stuff that exists and is useful. And I started looking at models, and I saw what Larry Abbott did, and we worked research-wise with a lot of these guys, and because the computational end is something that we're very close to, and X.J. Wang, who's now at Yale, Larry's now at Columbia, Chaim Sampolinsky is both Israel and Harvard, and Nicholas Brunel over in France, and the guys over at Courant like David Kai and Mike Shelley and so on. I like this model particularly. It's not up there for any reason. I happen to have extended my work on it. Maybe I related it more. I'm not going to go into any details on the field theoretic and spike firing aspects of it. It is interesting, you know, corticothalamic and the whole looping that goes on there is something that's been studied quite a bit, and a lot of approaches reduce to very similar things, which is a good thing. And so you can wind up with some linear differential equation approximations, but it's really delayed differential equations in non-local regions that give the nonlinearity, lead to the bifurcations, and the bifurcations are very interesting biologically as they are in physics. Whenever you get a phase transition, you get something really interesting happen. Yes, it only gives you the boundaries, but once you get the boundaries, you can try to fill in the states. So I began with some other people looking to extend this into some state vector formulation more generally. Of course, there's been loads of work done in this area, and more to come, and I think we'll get at some interesting things. So I forget who used the word that popped out of my mind what I'm trying to pop here, and that is that who knows what a bifurcation implies behaviorally. And what I think is exciting is actually connecting, perhaps not neuronal, because I don't believe that. It's collections or populations of neurons and perhaps columns or whatever. But as you go up those levels to the behavioral scale for humans, that is a very exciting thing. How do you connect all of that together? And it will indeed be connected. So it could very well be that we're looking at mathematics from either from a double pole or double pole zero structure that resonates, or nonlinearly in a bifurcation that actually can give you the aha in solving a problem. And a conscious pop, so to speak, happens as you get a temporal accumulation that builds in cortex, and then at that point you get a ramping to threshold and a popping that's happening in adjacent regions and so on. Maybe. Not saying it's so, but these are things that you can almost taste and feel in the mathematics. That isn't science, so we're now really trying to dig into that. But it does make it very exciting and very interesting, and the modeling is there. It's amazing that it's there, that you can do these models and simulations. There is progress, and in fact, in the last few years, I think more than I had seen previously, so good stuff's going to happen. Let me move that over to looking at into the harder technology, from the science to the technology and the combination of the two. There's a lot of way to look at this, but I look at it as from an anthropomorphic sense. But if you flip it around, Terry Sinofsky and Christoph Koch like to call it a telluride neuromorphic systems. IBM used to call it autonomic systems. Everyone had their own name for these things. That's kind of the flip side. We're using cognitive computing. Whether that's the same or not, I don't know, but these are next-generation computing paradigms, and they're going to have pieces in it. And the pieces are not in the head. I should have drawn some squiggly arms and legs, which I've done before, and seeing what happens in a sense of augmented cognition, which is one of the first things I think will happen. Before we actually have spiritual machines a la Kurzweil 50 years from now, you're seeing augmented cognition starting to happen. Reverse engineering of brain functions is beginning to happen. The pieces that play into it, that are adjacent to it, I think are smart sensor networks, wearable computing, mobile and wireless computing, micro-optical electronic mechanical systems, and so on, the whole nanotechnology world. And specifics that are coming really from more the brain side. Okay, cortical microcircuits, as we understand this, as we understand neuronal networks, as I prefer to call it, or EEG, wireless dry electrodes, so you can have mobile and wireless EEG done to look at the brain dynamics. You don't sit there as they make you. I just did some testing the other day. I was part of some experiment that we were doing, and I'm not interested in doing it again. Okay, so if you can do it in a different way, maybe a little piezo for better contact and dry electrodes, which is happening, you can move around. You move as a human. You're mobile. Your motion matters, and they all connect together. So there are science and technology pieces that are already converging with implications going forward that will imply computing paradigms of the future, and I think help also in the reverse direction of understanding the brain. I did my best to put down a bunch of companies, and this is my apology in advance, because this is so far from complete. I just put down some. Obviously, some of the guys on the panel are listed there. Softmax is basically a company that for about 5 years spun off from Salk and UCSD doing ICA, basically using ICA algorithms, and for 10 years those algorithms have been getting better and better. So noise cancellation and ASR, and you'll hear what Lloyd Watts does at his company, Audience Inc., are approaches to try to, by blind source separation using ICA, eliminate noise. Never mind noise cancellation, which I think is what it says and never got changed. It's really noise elimination. And we did at Symbol a fuzzy logic barcode scanner. This goes back at least 7, 8 years ago, and I am very proud. And if Professor Zada was here, I would show it to him, of a T-shirt. It's not a T-shirt, it was a sweatshirt that he signed. Because if you remember back to then, just like AI, a lot of things that start early They're just not there. So people poo-poo them, are more disciplined in science and technology. But the fact is there's a basis there. It's just not there yet, just like everything that we're doing. But you see little sparkly things pop out that do make sense. So people in AI who totally poo-pooed it, give it a different name, 10, 20 years later, good things happening. People were saying that about fuzzy logic, waste, silly, whatever. We built a scanner for low contrast barcodes and for all types of situations where the printing was very bad and the substrate was horrible and you weren't getting diffuse scattering, which you need coming back into the laser scanning system. And with all the analytical things we did, we still weren't quite there. And people wanted. They wanted longer distances. They wanted cans that were misprinted. And it was the job of the technologist and the company that was going to do business in that space to provide the job. And fuzzy logic was indeed helpful. So these things really do come up. This is a fun one for the future. Neurofocus, I think, is a company that Bob Knight at Berkeley is associated with. Neuromarketing. Many of you read lots of New York Times articles about that. It's a fascinating topic. I want to throw that one onto the table for you. I claim it's shopping. If you read Dijksterhuis's article last year in Science, I think it was March 06, on making the right decision, okay? So understanding the brain leads to decision-making things in our lives and in a lot of different quarters. And I think that applies to problem-solving as well as decision-making. Clearly, many of these companies, Numenta is really not described well. It's really Bayesian belief networks. And MERL is Mitsubishi. So Mitsubishi in the US has a belief propagation algorithm, movie recommender. Posit Science is actually showing at least 10-year reversals in a large percentage of cases by using computer gaming, computer-activated gaming. And then there are generic things, and who knows what's going on at Amazon, Google, Netflix in terms of monitoring and choices and predictability. And certainly we know what Amazon's doing on books and doing a good job on it as well. So there are lots of companies in areas. Anderson mentioned yesterday Aptima that he's teaming with in applied cognitive science. You know, it's too much to know. Rhizome does event-driven architecture, which is now coming on big time. So these are specific companies really happening using the science and technology that is becoming real. I happen to put this up to focus on a little bit because I know more about it. The 7th International Conference in ICA is in London in September, by the way. Audio separation, biomedical data. Yes, EEG, but also cardio. Why not outright to the heart and so on, and EKG that with its sparseness and wireless and so on, and then you've got something where your cardiologist is monitoring you wherever he is when you're working out in a gym, etc. And BCI, I know most people, or many people call it BMI. The guys I know call it BrainComputer Interface. Same thing. Again, cognitive computing, computational neuroscience. Flip sides of the same coin. The next frontier of what's happening, this was not meant to be literal, that it's the only next frontier, and it certainly relates to, though, I think, some of my points that I think are worth expressing on brain science converging with computer science, you know, both progressing in many ways, and you look at it and brains are active. Certainly the multi-scale, multi-level part is clear. The dominant multi-level model is computers today. Collaboration is going to be needed, no question. But not just people, yes, people collaboration, I'm sure company collaborations ultimately, but across time scales, across measurement techniques that are all over the place, all of them bringing something, and across models that are very different than one another, but I've noticed them starting to give very similar results and looking like a lot of things in physics, you can attack it in different ways. And I'll mention that later or bring it up as a question I want to ask the panel. Here's a big one to me, the hammer-nail thing. If you hammer, everything looks like a nail. You work molecularly, that's what everything knew before. If you work on a neuronal level, that's what you're thinking. If you work on a behavioral level in psychology, that has got, it can't stop because it's human nature and it's not going to stop so quickly. But the next generation of that is really got to be move into something that really curtails or not eliminate, but scale chauvinism is the best term I've heard for it, and it really has to be decreased so people can work across levels. Last slide is the economic impact in terms of the long view of things. not literally mentioning Boston and San Francisco, but I do think that kind of thing is happening. I think that there is a potential here of neuroscience and cognitive computing attracting a wide range of industries. It's not just the question of Microsoft and Google and Intel for the future. It's Pfizer and Merck and Amgen and so on. I think it's a tremendous opportunity. I think it's very exciting, and that's what our panel is really all about. It is a panel that has people interested in the corporate commercialization world, which depends on the science world, and the science is inextricably linked to it as well. Thank you. I'm going to take my